Okay. Hello to everyone. Hello to the people on YouTube. Hello to my fans. My mom. My mom. I would like to introduce to Kuljeet Singh Saddal. He's a PhD student in the Czech University and the
Astronomical Institute of Czech Sciences.
That. And he's working in Astrospheres and the stellar wind of these kind of stars. So today he will talk us about that and his research about his stay in Valparaiso and Santiago. So with that, I would like to present Kuljeet. Thank you.
Thank you, Ignacio, for the nice presentation. So I would like to start my talk by introducing what an astrosphere is. So astrosphere in general represents the interaction region between the stellar wind and the interstellar medium. So here this image specifically shows an astrosphere for the Sun, which is called as the heliosphere, but qualitatively it should be the same for any star. So we have the star here as the yellow dot in between, and the star typically has a radial stellar wind outflow, which is supersonic. Similarly, we have the interstellar medium coming from the right in a laminar-like flow, and the interstellar flow can also be supersonic. Now, to decelerate from supersonic to subsonic, the stellar wind has to go through a shock, and that shock is the termination shock which we see in this caricature. Similarly, the interstellar flow also has to decelerate from supersonic to subsonic speeds, and that occurs at the bow shock outside. And then the astropause or the heliopause here is the boundary which physically separates the two flows. So inside the heliopause we'll have the stellar wind, outside we'll have the interstellar medium, and they separate out at this separate, it's called as astropause. And what we are interested in is solving the magnetohydrodynamical equations close to this point here, where we assume that the velocity and the magnetic field go to 0. So I would first introduce what magnetohydrodynamical equations are and linearize them, since we are solving very close to a point. Everything would be Taylor expanded and hence linearized. Then we'll see how this linearized fields look like in 2D, and I will present my analysis briefly in 2D, but we won't go into much detail because we are interested in how the analysis looks like in 3D, but the methods in 2D and 3D are similar, but in 3D the expression gets much more complicated, so it's harder to follow. Then we'll discuss some special solutions which we get from the analysis in 3D, and then I'll conclude my talk. So the equations of magnetohydrodynamics, they describe the motion of a conducting fluid basically. So a conducting fluid in the presence of electric and magnetic fields. So when we talk about electromagnetic fields, we first need the Maxwell's equations. So we use the first, second and the fourth Maxwell equation to form the equation of magnetohydrodynamics. Second, since we are talking about fluids, we need the equation of fluid dynamics. So here the first equation is the continuity equation, the second equation is the momentum equation. And third, when we talk about conducting fluids, we generally talk about Ohm's law. So in the ideal case, this resistive term goes to 0, but since we will be dealing with resistive magnetohydrodynamics, we keep this term. So you can take these equations, you eliminate the electric field and the current, and what you end up getting is the equations of magnetohydrodynamics which we will solve. So as the next step, it is very useful to make these equations dimensionless, because then we remove the scale of the problem, and our theory would be applicable for plasmas at any scale, for astrophysical plasmas or for laboratory plasmas in general. So that is scale invariance. So to make it dimensionless, we should have the typical scale of the system, we should have the typical values of magnetic field and the plasma density at some representative position, which in our case is the apex of the astropause. This is the point which I indicated before. And these values can be obtained typically through observations or through literature. Then to have the characteristic time scales, we first need to find the characteristic velocity scales, which in magnetohydrodynamics is chosen to be the alpine speed. And alpine speed can be determined using the characteristic magnetic strength, magnetic field strength, and the plasma density. Once we have the characteristic, so the characteristic time scale will be just the characteristic length scale divided by the characteristic velocity. Once we have the characteristic length scales and time scales, the differential operators also have to be modified, and finally the dependent variables also are modified by dividing by the characteristic scales. Notice here that the characteristic pressure is the ram pressure of the gas. So we write our expressions in the bar quantities, but we don't keep writing the bar again, so because it gets very tedious to write the bar every time. We will just assume that the equations are dimensionless from now. Okay. So now since we want to work close to, in a small neighborhood close to the apex, everything can be Taylor expanded. Yeah? So fields close to the null point can be Taylor expanded. And we work under the assumption that the point where the velocity field goes to 0 and the point where the magnetic field goes to 0 coincides. Okay. So as long as fields can be Taylor expanded and the velocity null point coincides with the magnetic null point, our theory is valid. So it's quite general in that sense. So we know how to Taylor expand for a scalar. Any scalar function f of x can be Taylor expanded at a point A. The Taylor expansion would look like the value of the function at A plus the first derivative evaluated at A times x minus A, and so on and so forth. We can similarly evaluate also vector fields in this way. So the velocity would be value of velocity at the null point, which is the origin, and the value is 0. So we don't have this term. Then for vector fields, this term would look like a matrix. It will be a matrix of derivatives. So this will be a 3 cross 3 matrix which looks like this. And this is called as the Jacobian. Times x minus a would become a column vector x, y, z, which is represented by r in this case. So similar to velocity field, the magnetic field can also be Taylor expanded, and the pressure will also be Taylor expanded. But since the pressure appears as a gradient, the pressure can be of second order in spatial variables, whereas for velocity and magnetic field we keep only the first order terms. Right. So this matrix V, we take the most general form of any matrix. We have 3 cross 3 matrix with general components, and the matrix B though takes this very specific form, which I will come to later in later slides. So our aim in this presentation would be, given a magnetic field, how does the velocity field look as a solution of the magnetic equations? Okay, so let's get into it. Before doing that, we'd like to first see that in general how the vector fields of the form V equal to some matrix time R looks like in 2 dimensions. So the field structure depends on the eigenvalues of this matrix V. So in 2 dimensions we have 2 eigenvalues, and in the table the left column represents the structures when the eigenvalues are real, and the right column represents the structures when the eigenvalues are complex. So when we have real but eigenvalues have different signs, we get a saddle point. So the field lines look like hyperbolae, and they come in along one asymptote towards the null point, and they go out along the other asymptote. So the field lines come in and go out. Then if both the eigenvalues are negative, then all the field lines go into the null point, and then the null point acts like a sink. So all the field lines are going into the null point. Similarly, we can have a source where the eigenvalues are real and positive, so everything is emanating out of the null point, here, as you can see here. Then if the eigenvalues are complex but have negative real parts, then we have a spiral sink. If they have positive real parts, we have a spiral source. And if they have no real part, only complex, then we have these concentric circles. We will see that our matrix under the incompressibility condition becomes traceless. And the trace of a matrix is nothing but the sum of the eigenvalues. That just means that lambda 1 plus lambda 2 equals 0, and lambda 1 and lambda 2 cannot have the same sign. So the only configurations we can have is the saddle point, which is shown here, or the center. So we call this an X point because it looks like an X, and we call this an O point because it looks like an O. Okay. So now the form of the magnetic field. So the form of the magnetic field was suggested by Parnell in one of her works, and in 2D it looks like this. So B and minus B ensures that it is traceless, right? And the field can in general be given by three parameters, B, Q and Jz, where Jz is the Z component of current. Right? I understand that I said 2D, and there is a Z component because cross products are defined only in 3D and not in 2D. Okay, so to find the structure of B, we first need to calculate the eigenvalues of B, and they take this simplified form where Jc, the threshold current, can be defined in terms of the potential form. Sorry, this is for B square plus Q square. In the paper they use P and I use B, so there is some confusion. Yeah. So now we can see that when the threshold is greater than the Jz value, we have X points which correspond to these two scenarios. When we have the threshold value equal to the current value, the eigenvalues go to 0, the rank of the matrix drops, and we get 1D fields. And when we have the threshold value less than the Jz value, then we have O points because the eigenvalues become complex. With this in mind, we will now go to the magnetohydrodynamical equations. So these are the equations we would like to solve. So we substitute the Taylor expanded velocity and magnetic fields into these equations, and we get this. So the first equation is nothing but the momentum equation here. Notice that there is no pressure in this equation because the pressure was second order and the pressure matrix was symmetric. So there is a property of symmetric matrix that if you take the transpose of a symmetric matrix, it's the same matrix. So you can make this into matrix form, take the transpose and subtract the same equation by its own transpose, and you get this equation. Then the condition of incompressibility basically means that the trace of V should be 0, and that's why V can only be saddle points. This is the definition of current. This is trivially satisfied because of the form of B. And instead of using the induction equation, we use these two equations separately. So we'll use del cross E equal to 0 to write E as a form of as a gradient of a scalar potential, and then we'll solve the Ohm's law equations with this. So let's get into it. So the way we'll do this is we first since the curl of E is 0, E can be written as the gradient of a scalar potential phi, would be in general a function of x, y and z because current has a component along z. And then we solve the Ohm's law for each component. So Ohm's law is a vector equation, so it will have three equations for three components. So the first equation would be the partial with respect to x plus the velocity magnetic component equal to 0. Here notice that Bz and Vz is 0. So this expression basically means that the partial of phi with respect to x is 0, or phi is an explicit function of y and z. Similarly, in the second equation, this part is 0, so partial of f with respect to y is 0, so phi should be an explicit function of z. And you can use that in the third equation. Now, notice that phi has to be an explicit function of z. But Vx, Vy, Vy, Vx, they are all functions of x and y. Eta is assumed to be a function of x and y. Jz is constant. So this term can only be a constant to the highest order. And this constant we represent here as Ez. Right. And secondly, since V is linear in x and y, V is linear in x and y, the product would be quadratic in x and y. That just means that eta can be a maximum of second order in x and y. And it can be straightforwardly calculated by rearranging terms, and it looks like this. So here I use colors because otherwise if I write it in black it is very hard to read, especially in 3D. So here the blue are for velocity elements, the red is for magnetic field elements, and the black is everything else. But, okay. So we would now like to get the relations between the velocity field elements in terms of the magnetic matrix elements. To do that, first we use the equation of incompressibility, which just says that V22 is minus V11 because V11 plus V22 should go to 0 in this case. And then the momentum equation, which is of this complex looking form, is an antisymmetric matrix because some matrix is subtracted by its own transpose on both sides. So if you do that, your resultant matrix becomes antisymmetric, and antisymmetric matrices in 2D has only one independent component. So we get only one constraint on V21. So that's it. We can write our velocity. We get two sets of solutions corresponding to plus and minus, and we can write our velocity matrix in terms of two free parameters, which is V11 and V22, and magnetic field parameters. So I would not discuss the solutions for 2D, but we'll use the same procedure in 3D and discuss some special solutions in 3D. So let's get to 3D. We get back to this slide. We would like to express this matrix in terms of the elements of this matrix plus some free parameters, and we will see that even in 3D what we end up getting is we get four sets of solutions for V in terms of two free parameters and the magnetic field parameters. Before starting with, it is useful to see how the solutions of equations of the form. Solution of equations of the form this looks like in 3D. So now here the matrix V will in general have three eigenvalues, lambda 1, lambda 2 and lambda 3. Right. So if the real parts of all the eigenvalues are positive, we get sources. If they are all negative, we get sinks. And if all the eigenvalues are real, the configuration looks like this. Everything just falls directly into the null point. This is a radial sink. Similarly for a source, all the arrows would be reversed. Everything will go away from the null point. And the second configuration which is possible when two of the eigenvalues are complex conjugates is the spiral sink, which you can see here. But this is not very interesting because we know that V has to be saddle points. So let's discuss saddle points first. So saddle points are formed when not all eigenvalues have real parts with the same sign. And in 3D, the saddle points have a rather more complex structure than 2D. They are just not hyperbolae, but they have two components. First is a plane, which is the xy plane, which is represented here, and another would be a line, which is the z-axis. So this xy plane is known as the fan plane, and the z-axis is known as the spine line. So what would typically happen if all the eigenvalues are real? For example, we get this configuration. Say the two of the eigenvalues are negative and one eigenvalue is positive. In that case, the eigenvectors corresponding to the two eigenvalues define the equation of this plane, and the field lines in this plane go into the null, right, as you can see. And the remaining eigenvalue, which was positive, the field lines will go along the z-axis, along the spine. So basically the field lines will come from somewhere and go along the z-axis. Similarly, if you have complex eigenvalues, you will have similar kind of behavior, but now your field lines will be spiral. Okay. So similar to 2D, in 3D, Parnell suggested a structure of the magnetic field. You can compute the eigenvalues. Again, we have this form where you have a square root of jc square minus j parallel square. Parnell imposes some constraints so that this eigenvector is always negative and these two always have positive real parts. Yeah. This is because the spine will then be fixed at the z-axis because the eigenvector corresponding to this eigenvalue is the z-axis. Okay. So this is how the field structure looks like. So when the absolute value of j parallel is less than the threshold, we have real eigenvalues, and when the current goes to 0, we have this nice symmetric configuration where the field lines are radial in the fan plane, and the field lines come in from the spine and go out in the fan in this case. Also note that P is nothing but B. And when current is not 0, there is this preferred line in the fan plane along which the field lines flow. So we don't have this nice radially symmetric structure anymore when the current is not 0. Similarly, when the eigenvalues are complex, we get spiral-like structure, as we can see here. And when J parallel equals to the threshold, then the eigenvalues do not exactly go to 0, but 2 of the eigenvalues become same. So we get a borderline between the spiral flows and the radial flows, and they call it the critical spiral. So now this the equations of magnetohydrodynamics for this scenario was calculated by Tita van Horne in 2000 for a special case of constant resistivity. Right. The flow was considered to be incompressible, and they solved the stationary MHD equations, like we saw in 2D, but they solved the induction equation and so forth. So equation 4 and 5 will give us 7 linearly independent equations for 9 variables. So that means that 7 of the velocity components can be written in terms of the magnetic field components, as you can see here, and 2 free parameters, which here are chosen to be V11 and V22. Also note that here as a consequence they have V13 going to 0, which will be important for our analysis, but we will come back to this later. Okay. So once you have this prescription, you can substitute in the momentum equation. The momentum equation is an antisymmetric matrix in 3D. So that means it will have 3 independent components. So 3 equations for 2 parameters, and these are the solutions they obtain. The first solution is the trivial case where the V matrix is plus minus B matrix. So the velocity field is always parallel to the magnetic field. And the second solutions which they obtain was called the spiral field crossing flows, and they only exist for complex eigenvalues, but we will not discuss much about this for now. Other important consequence is that the fan and the spine, for velocity field and for the magnetic field, they always coincide. They can never have an offset in this analysis. So now we'd like to solve the same equations, well, in a slightly different form, but for non-constant resistivity. So now here we'll assume that our eta can be any general polynomial in x, y, and z. Okay. So instead of solving the induction equation, we solve these 2 equations separately as in 2D. So everything remains the same. And once you have the prescription of velocity field in terms of magnetic field, you can calculate the pressure in terms of the magnetic field elements and 2 parameters. So again, electric field is curl free, so it can be written as the gradient of a scalar potential. And now we have the Ohm's law, but here it will take a slightly more complicated form. We can no longer solve it in one line. So first our aim would be to calculate phi, but we are not interested so much in phi. We will try to calculate eta because eta is relevant for our analysis, and we will see that this eta will give us some more constraints on the velocity matrix elements. So first we look at the equation 14b. V is linear function in x, y, and z. B is linear function in x, y, and z. This just means that the right hand side is a second order polynomial in x, y, and z. So it is easy to integrate this equation with respect to y. You integrate and you obtain this expression. But now since the derivative was partial with respect to y, the integration constant would be an arbitrary function in x and z. So we need to fix that. So to do that, we again get back to Ohm's law. We see that we can multiply 14a by j parallel, we can multiply 14c by j perpendicular, the right hand side becomes equal. We can equate the right hand sides, hence the left hand sides, and what we end up getting is this equation. So this equation can be directly solved in Mathematica, for example. And you get this expression for f of x comma z, where c now is an arbitrary function in j perpendicular by j parallel x minus z, and we don't know how to deal with this, so we choose the most general ansatz for c. So most general ansatz for c, since everything is of third order in spatial variables, so and everything locally is Taylor expanded, the most general ansatz would be a third order polynomial in j perpendicular x minus j parallel z. Later we would like to fix this coefficient somehow, C1, C2, C3 and C4. Well, C4 goes to 0, so it does not matter. But C1, C2 and C3 has to be fixed. Has to be done later. So 18 with 17 substituted in 15 gives us the expression for phi. But now we want eta. So there are two methods of obtaining eta. So the first method is substituting in the first equation and then rearranging the term. It looks bad, I know, but it's just a second order polynomial in x, y and z, where each coefficient is a function of the magnetic field parameters and the velocity field parameter. So alternatively, we can substitute phi in the third equation of Ohm's law, again get an expression for eta. And eta is a physical quantity, it should be unique. So these two expressions should be the same. So we have to equate these two equations. That basically means that the coefficient of x square here should be the coefficient of x square. The coefficient of xy should be same as the coefficient of xy, and so on and so forth. So it gives us 6 relations, but 3 of them are trivially satisfied. So we get only 3 relations out of this. So you can notice that the relations are linear in V. So we get 3 equations from the resistivity which are linear in the velocity field components, and the equation of incompressibility which we did not take, which we did not consider until now, imposes another constraint. So we have 4 constraints for 9 velocity matrix elements. That basically means that we can express 4 velocity matrix elements in terms of other 5. So that's what we do. We choose the independent parameters to be the first 5 elements of the velocity matrix, and yeah, we can just solve the linear equations and express each term in terms of the first 5. Yeah. Now we also have the momentum equation, which I said before is just 3 equations for the 3 quadratic equations in terms of the velocity and magnetic field parameters. So now we have 5 parameters, V11, V12, V13, V21 and V22. We have 3 equations, so we can write 3 parameters in terms of other 2, and that's the solution. We get V12 in terms of 2 free parameters, V13 and V11. Yeah. So we choose here, instead of V11 and V22, the independent parameters to be V11 and V13. And the motivation to do that is, in the previous work by Tita and Hornick, which I presented a few slides ago, they explicitly got V13 to be 0. So if in our analysis we put V13 equal to 0 and we get back the solution for the we get back Tita and Hornick solution, then our theory would be stronger basically. So the another advantage of using V13 is you can see that V12 and V21 take this form where it depends only on V13 and not on V11. Okay. And V22 depends on V11 and V13. It takes a more complicated form, so I don't write it in this presentation, but we will see it later. So we are interested in the class of solutions where V13 goes to 0, because that's what Tita and Hornick obtained. So here I forgot to mention that we have 4 sets of solutions corresponding to plus, 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 minus, minus, plus and minus, minus. So we get 4 velocity matrices which we represent by subscripts 1, 2, 3 and 4. When we put V13 equal to 0, the 4 sets come down to 2. 2 of them become equal. So we have V1 equal to V3, which is of this form, V2 equal to V4, which is of this form. And this form is nice because you can see that all the non-diagonal elements here are the same as the velocity, the magnetic field. Only the diagonal elements are different. Like Q minus J parallel by 2 is same as Q minus J parallel by 2 here. And that is true for all the non-diagonal elements. Yeah. So when we substitute V11 equal to 1, we get back the trivial case. We get back the case where the velocity is parallel to the magnetic field or anti-parallel to the magnetic field. And we also get that if we fix C1 and C2 to 0, we get constant resistivity. So this is nice. The analysis until now looks nice. The problem is, then this matrix should be similar to the second solutions which they got, which it is not. Yeah. So we don't know why yet. We are still analyzing, but at least to some extent this theory holds. Okay. So now we'd like to see how the field lines look like for this set of solutions where V13 is equal to 0. Right. So now to plot we need to fix the magnetic field parameters. So we choose this value so that the magnetic field is real. That just means that it has real eigenvalues. Right. So the fan plane, which is represented by purple here, is determined by the eigenvectors corresponding to the first two eigenvalues, and the spine line, which is the thick purple line, is the z-axis, which corresponds to the eigenvector corresponding to this eigenvalue. Okay. Now we would like to see how the velocity matrix, the first set at least, looks like as a function of V11. So we see that now velocity also takes a very simplified form, the velocity matrix, it's not very complicated, and the eigenvalues take this form. Here we have a square root, we have a polynomial under the square root, so it was very tempting at first to think that they can have complex eigenvalues because the polynomial can go negative, but it turns out that this polynomial never goes negative, so we only have real eigenvalues. So this figure here shows the parametric plot of the three eigenvalues with respect to the free parameter V11. So here notice that the first eigenvalue goes to 0 at x equal to 0.4. The third eigenvalue goes to 0 at x equal to at V11 equal to -5. Then the second eigenvalue never really goes to 0. But eigenvalues going to 0 basically means that the rank of the matrix drops by 1. So we will have 2D configurations as well, and we call them degenerate cases. So let's see how the solutions look like. So first case where V11 is less than -5, we have the eigenvalues, the first eigenvalue negative, the second and third eigenvalue positive. That just means that the fan plane is determined by the eigenvectors corresponding to the second and third eigenvalue, and the spine lies along the eigenvector corresponding to the first eigenvalue, which is z1. And since the first eigenvalue is negative, the spine is a stable surface, which means that the field lines will come along the spine, as you can see here, and go away in the fan. Okay. And this figure here shows the orientation of the separatrices of the magnetic field and the velocity field. So everything in purple is the magnetic field, everything in yellow is the velocity field. So magnetic field is constant, it takes the same form, does not change. But here the velocity field is radial null, and this is something which we did not obtain in Titov and Hornick solution. When I said Titov and Hornick solution, they always had the yellow line coinciding with the purple line and yellow plane coinciding with the purple plane. For us, we get different solutions. Then case 2, we have degenerate cases. In this case, one of the eigenvalues, the third one, this one goes to 0. So the field lines look like x points, parallel planes of x points. We have not plotted them here. Something interesting happens when we for -5 phi less than V11 less than 0.4. So degenerate was when V11 is equal to 5. When V11 crosses this point, now we have two of the eigenvalues which are negative and one which is positive. So in this case now, the spine will correspond to the eigenvalue corresponding to the second eigenvector, and now the second eigenvector is positive. That means now spine is the unstable subspace. So everything is coming in from the fan and going out along the spine. So the configuration somehow flipped. We have the field lines coming in from the fan, going out along the spine. Then again at V11 equal to 0.4 we get degenerate case. And finally when we cross the degenerate case, we again have two of the eigenvalues positive, one negative. That means the spine lies along the eigenvector corresponding to the negative eigenvalue, and that is the z-axis in this case. So the purple line and the yellow line will coincide. And again the spine becomes the stable subspace. So now again spine is getting the field lines towards the null point and fan is driving them away from the null point. So there is a flip which we see each time for degenerate cases. Right. And this set of solutions will, for when V11 equals to 1 will also accommodate the trivial case. When these two will become exactly the same. Okay, so that was for the radial null. Let's briefly look at what happens for the spiral null. I will not plot things here. But we again fix the magnetic field parameters so that the magnetic field has complex eigenvalues. In this case, we can determine the structure of the velocity field. Yeah. And you again have a polynomial inside a square root, except in this case it goes negative for certain values of V11. So now the velocity structure can be summarized as follows. It will be radial for V11 is less than the first root. It becomes complex, or the eigenvalues become complex, or the field becomes parallel where V11 is between the two roots, and it again becomes radial for V11 less than V11 greater than the second root. So now for a spiral magnetic field configuration, we have radial velocity configurations possible. So we would like to see, in general, we would like to find the criteria, like given a spiral or a radial magnetic field, when do we get a spiral or a radial velocity field, which is not done yet. So that is a part of the future work. So we solve the linearized and resistive magnetohydrodynamic equations in a region close to the null point, and the solutions we saw that were described in terms of magnetic field parameters and two free parameters. So now, as the next step, we'd like to find the criteria, or we'd like to find a method to characterize the solutions somehow. Because now we only saw the special case where V13 was 0, and only for the first set, not even the second set. And it is giving such rich solutions. So we'd like to categorize all the possible solutions in this analysis. And secondly, after obtaining the velocity and the magnetic field structure, one can, for example, calculate pressure, one can estimate density, and hence calculate temperature. And with the temperature, we can calculate what is known as the emission measure, or basically the flux per unit solid angle, which we measure from the point. Yeah, and that I would like to then compare with simulations, which is my work right now with Ignacio. That I like to simulate the same system using a magnetohydrodynamic code, and to calculate emissions in this region, and then comparing it with the calculations which I made. So that would in some sense determine the field structure at this point, which we cannot directly measure. And we would also like to compare it to the observations with the theory. So that's it. Thank you.
Okay, we have time for questions. Questions?
Okay, I have a question. This calculation based on the linearization of the MHD
Yeah.
equation. And did you try any simulation without linear relation?
That is what we are currently, that is my work with Ignacio.
Okay.
To first to do this in magnetohydrodynamical code to simulate this problem, and then to see how well it agrees with the theory.
Okay.
Yeah, so that is still a work in progress, but yeah, that is one of the things which we need to do.
It looks like the only nonlinearity of in the equation is from the Navier-Stokes equation.
Yeah.
Nothing else.
Nothing else. Yes.
So it looks quite straightforward to solve it.
Yeah. Yeah. It looks quite straightforward, but yeah, basically the Navier-Stokes equation gives the nonlinearity, and the problem is the solution was straightforward, but this part is proving difficult.
Okay.
Yeah.
Or
categorizing the solutions. Otherwise, the calculations were pretty straightforward.
I see.
There were only a few difficulties like choosing the free parameters, because that choice which we made took some time. Because if you take the standard, if you choose the free parameters same as θ1 only, as they did, v11 and v22, the equations look horrible. Yeah, and then it was very hard to even study the solutions. In this case, we do find a nice way to represent the solutions, but not yet to categorize.
Okay. So in reality, the force term in the Navier-Stokes equation only the gradient force, no viscosity.
Also the J cross beta. That also contributes.
Is there any viscosity?
No viscosity.
No viscosity.
Because here typically for astrophysical plasma, the density, the number density goes as 10 to the power minus 24.
Okay. Plasma.
So yeah. So the plasma can be more or less assumed as a first order to be collisionless, and we need not include viscosity effects for this.
Okay. So you don't need to worry about the turbulence anymore.
No, not at least. Even if you do, I don't think the contributions would be very significant in this case. Again, because the density is very sparse.
Okay. I see.
More questions? Here? What kind of observations do you need to compare your results?
We just need the flux per steradian, for example.
Okay.
And you can obtain them from Herschel, you can obtain them from the survey which we already have done in H-alpha.
Okay.
So we have the images, they have to be flux calibrated. But we typically look at the flux value from the Bow shock.
Okay.
Yeah, and that is the observation. So we already have all the observations, we just need simulations to compare it.
Okay, so we need to work in it. Okay. Great. Any other question? Amar?
Yes. Can you have another form of the magnetic field? Because you put an...
This form is very general. By choosing this form, what we have fixed in reality is just the coordinate system. This form was chosen such that the orientation of the magnetic field is such that it looks like this, basically. That the z-axis is always corresponding to the spine. Yeah. And fields are coming in from the z-axis and going out of the fan plate. Yeah. So you can choose a different form. In the end, it only depends on the eigenvalues of the matrix. Oh, that's it. Yeah.
No more questions? No? Okay. Let's thank again Kuljeet.
Thank you.
So now we have a cocktail in the center.